Oh, where yeah, the derivative at that point is equal to the average.
Yeah. Okay, good. It happened. Good. Okay, yeah. So we have, this is like the story of me running the half marathon or whatever, however we want to think about it. The New Jersey Turnpike story. If you have some function, then there is, on any given interval AB, there is somewhere where the slope of the tangent line equals the slope of the secant line. That's the geometry way of saying it. Okay. But the deep way of saying it is that there's some point on every interval AB. There is a point at which the instantaneous rate of change equals the average rate of change. Okay? There's a point where the instantaneous rate of change equals the average rate of change. And over here in the mean value theorem for integrals, what it says is that if given some kind of function, there is a place, there's somewhere at which the function has its average value. Did I do that right? That's decent. So that point is 1 over b minus a times the integral from a to b of f of x dx, which is a number after all. And the mean value theorem for integrals says there is some special point, or more than one, at which the function obtains its average value. Okay, but that's just math mumbo jumbo talk. Let's talk about the real understanding of this involves physics. Okay, watch this. Here, it's most natural to talk about a position versus time curve. And what does the mean value theorem for derivatives say now regarding this position versus time curve?
There's some point at which your velocity.
Carmela?
At some point, your instantaneous velocity equals your average velocity.
There's a point at which your instantaneous velocity equals your average velocity. In other words, there is a particular point at which the rate you are going at that point is the rate such that if you just went at that rate the entire time, you would have achieved the same change in position. Do you want me to say that one more time?
Yeah.
I'm going to say it one more time anyway, Brian. There is a certain change in position that happens from A to B. It's the height that I gained, right? I could achieve that height in a variety of ways. I could achieve that change in height by going at a constant rate. That would be the secant line. Or I could achieve that change in position by going at a variable rate. There is a special representative point, says the mean value theorem, at which I'm going at the rate I could have just gone at the whole time and achieved the same change. Okay. What does the mean value theorem for integrals say? Kind of the exact same thing. This is now a velocity versus time curve. And as we discussed last class, or at least I hope we did, that right we talked this out, right? How the area under a velocity versus time curve is like the change in position, right? So the area under this curve is going to give me, under this curve f, is going to give me the total change in position. What the mean value theorem for integrals says is that there is a special point c at which my velocity, because this is a velocity versus time curve, my velocity at point c is the velocity which, if I had just gone at that constant rate, I would have achieved the same position. In other words, the area under this blue line is the same as the area under this variable curve. Whoa. These geometrically are totally different from each other. This one says like there's some tangent line, which is parallel to some secant line. This one says that given some weird curve and finding the area under that curve, there is some special value that the function has where the box has the same area as that curve, right? So geometrically, these two things could not possibly be more different from each other. But if you were to just close your eyes and not look at the pictures and just listen to the words, this says there's a point, a special point, where my velocity is such that if I just went at that constant velocity the whole time, I would have achieved the same change in position. This one says there is a special point where my velocity is such that if I just went at that constant velocity over that whole interval, I would have achieved the same position. Whoa. Okay. we are at the precipice now of the fundamental theorem of calculus, and it's time for party hats. I feel like we should turn out.
One more second round.
By the way, what time is on that thing?
It is at 38 minutes.
Okay, that's about right. All right, good. Let's all come over here.